Hello, today we're going to be looking at the graphs of exponential functions. Recall in our work with functions that we look at going from the equation to the graph, and then we also look at going from the graph to the equation. Today we're just going to look at going from the equation to the graph. So here we have an exponential function. What makes it exponential is that it has a variable for an exponent. That's what will make it an exponential function. As we do with any function, we're going to begin with the table of values, and the table of values is going to begin with the y-intercept. The table of values is going to begin with the y-intercept and the x-intercept. So the y-intercept is when x is 0, and we can look at this graph easily enough here, or this expression easily enough here, and see that if I let x equal 0, I'm going to have 2 to the 0, which is 1. So that'll be the first value of our table, 0, 1. And then the next thing that we'll do is look at when f of x equals 0. And when f of x equals 0, we are going to be finding the x-intercept. So let's label our work, not just jump right into it. And then if I write this, 2 to the x is equal to 0. Now, I want to know what x is, and there's a way to solve for x. Hopefully you know, or you may know, that when you have a variable exponent for which you want to solve, the operation that will allow us to solve for that is the logarithm. Now, we don't necessarily need to use the logarithm here. We can look at this and examine it and think about what value of x would make this expression come out to 0. 2 to what power is equal to 0? And you may know that there's no power to which I could raise 2 that will come out to 0. So the x-intercept here is not going to exist. All right, now recall in other work with functions that there's always some key point that we're looking for, some key element. Perhaps we've talked about parabolas and how we're looking for the vertex. And recently, we've talked about rational functions and how we are looking for the asymptotes to be able to graph the rational function. For the exponential function, it is also an asymptote. We're going to be looking for the horizontal asymptote. And the assumption is that the horizontal asymptote of an exponential function is at y equals 0, unless there is some sort of shift. So let's just draw that in here, a horizontal asymptote at x equals 0. So what do I have here? I've got the horizontal asymptote at at y equals 0. I've got the y-intercept at 1. So I'll make my y scale like that, and I'll do the y-intercept at 1. Now what? Well, let's just find another point. If I let x equal 1, then I'm going to have 2 to the first, which is 2. And let's find one more point. If I let x equal negative 1, I'm going to have 2 to the negative 1, which is 1/2. And let's plot those points. 1, 2 is here, and negative 1, 1/2 is here. So if you look at the points here, here, and here, and perhaps if you know something about exponential functions, maybe you do, that an exponential function, an exponential increase is a slow, initially slow, and then eventually rapid increase. like that. And we use that term colloquially, just in common conversation. We say, oh, it's increasing exponentially, and that means that it's increasing really quickly. So let's go ahead and draw a curve that meets that criteria. Draw here, and then it's going to approach this asymptote on the left. I just highlight that to make it clear. So there's the curve there, and it's approaching the asymptote on the left. Let's look at another one. Graphing this function again, we'll start with our table, x, f of x, when x is 0. Think about it a little bit more. When x is 0, I'm going to have 0 for x here. So that's going to be 4 squared. It'll be a negative 4 squared. So it'll be negative 16 minus 3 is negative 19. So I've got a y-intercept at negative 19. Let's look for the x-intercept here. So when y equals 0, I've got the x-intercept, and that'll be negative 4 to the x plus 2 minus 3 equal to 0. So negative 4 to the x plus 2 is equal to 3. All right, now I can't do any other operation. I guess I can do the negative. Okay, so 4 to the x plus 2 is equal to negative 3. And again, the operation that I could use here would be a logarithm, but I don't need to use that to see that x is undefined here, because there is no power, there's no power here to which I could raise 4 to make this expression become negative. A negative power is going to create a reciprocal situation. It's not going to make the expression negative. So again, we have no x-intercept here. So we'll note that on our graph. Now, what's the next thing that we look for? We look for the horizontal asymptote. Now, what did I say back here? I said the horizontal asymptote, we assume to start with, is at y equals 0. So what's happening here, we assume that we have a horizontal asymptote at y equals 0, but what is there from some previous work that we did? There is a shift. So there is a vertical shift. There's also a horizontal shift, but that doesn't affect this asymptote. If I move the asymptote left to right, nothing changes. But if I move the asymptote up and down, that's going to create a change. So let's take this asymptote, and we will shift it down 3 units. 1, 2, 3. Based on this negative 3 here. All right, since I chose an inconvenient scale down here, I am going to move this graph over and then just find a couple of other points. So here are a few other points. So this negative 1 and negative 7 is here, and then here the negative 2, negative 4. So I've got those 3 points. If I plugged in a 1, I would have this negative 1 or 1, negative 67, which would be way down here. So there's the graph. There's the graph. And it approaches the asymptote on the left and drops down steeply. And there's going to be, of course, that y-intercept at -0, -19. And that's it. So we are going to want to look at what happens when there is an x-intercept. Logarithms are going to be helpful in that case, but this will at least get you a starting point.